So for the hands-on section, I'll request you to focus on the readme.doc file that has been in the Google Drive. So that will, I mean, if you have any confusion, I can update it here. So as not the txt on the readme, just the Google Doc file. So basically we will run the required software first. To run the software, you have to open a terminal. And we will run the Kafka zookeeper first, then followed by Kafka. So we'll go to the Kafka home directory and basically run the zookeeper server. Once the zookeeper server is running, open a new tab and go to Kafka home again. And type in Kafka, start the Kafka server with the command provided in the readme doc, bin Kafka server start.sh and with config/server properties file. To run Spark, open another terminal or tab and go to Spark home directory. Once you are there, type sbin/start all. It may ask you for the password. Just type in your login password. Now we will start the Elasticsearch. For that we will go to Elasticsearch home or eSearch home in this case, cd and run the Elasticsearch executable file from bin folder. Then we will start Kibana. We will first go to the Kibana installation directory that is specified in Kibana home and run the Kibana executable from bin folder. So the required software for this module is been running now. Now we will focus on the source code and see step by step how we collect the data, build the offline model, then produce the data in a streaming manner and also do the classification on the fly with the Apache Spark streaming, and how we can see the classifiers output in an aggregative manner on the front end with Kibana. So I have already imported the project into the PyCharm IDE. So we'll start with getDataPy file to get the training data from the Guardian API. To run that file, simply right click on that file and run get data. So it started downloading the data, and from now we'll explain how the get data portion works. So we'll be collecting 40 days of data. So we'll query and collect the data for each day 40 times. And we'll go back today. From today, we subtract 10 days and also subtract 50 days. So basically what we will be getting the data for today is 23rd. So the data should be within the range from July 13th. This is the end date, or 14th, depending on the house, and it should be 13th. These 40 days of data, we will get it as a for the training set. 3rd June? Yeah, 3rd June. 30 days. Yeah, it went up. Yeah. Okay. So in my case, it collected around 2,655 documents in total for those 40 days, and these documents will be used as a input to the classifier to train the model. Now let's focus on the get data file, where we put some arguments. Basically, you can specify the dates you want with the arguments that will be recorded as from date and to date. We have default values set for those parameters. Again, for mode, you can specify whether you want to download the data for each day for a particular interval, or you want to download the data for the whole interval. And with the list, you specify which section from the news article you want to focus. We focus on 4 of the sections that are specified in the default value, that is politics, society, media, and business. We then call the download method to download the data with the optional parameters we have. And if the collect mode is separate, that means you are willing to download the data for each day within the interval. It will download the data for each day by setting up the interval for 1 day. So this is the method we used to construct the URL for API call, so that we can get the appropriate data. So inside the API call, this is the target API you want to hit. This is the date you want to specify, from which date you want to start collecting the data, and to which date you want to collect the data. Your data collection will end. You also specify the section, that is tag, which is basically the 4 sections we shown earlier. And we always use a particular default key, but you can always sign up for a new key to use yourself. So once the download data operation completes, it creates a train.csv file where it stores the data. So now if you want to open the train.csv file, you should be able to see 265. There will be 2655 lines, with each line containing 1 article along with its label here. Now we will see how we can train the offline model. So basically we will be focusing on the training py file, but there are several other files which can be used to create models using different classifiers. So train.py by default uses naive Bayes, and you can use the decision tree, logistic regression or random forest using the appropriate files provided alongside it. So we will focus on the training py. So we will run the code first to see. To run the code, open the terminal and type spark submit training dot py. Sorry, in my case it okay. We have to remove it to lesson 1 lab solution. If you find that there is error on no such file or directory, you have to change the inside folder on lesson on lab solutions. So let's focus on the training.py, how it works. As we have already demonstrated in an example slide, you first create the Spark context with the SQL context that will be used to read the data, and you will read the data from the trains.csv. You will rename the columns to category and content respectively. You should be able to see the data towards the very top of the output maybe, but the output you are basically seeing the table that is this output. So you should be able to see all the predictions are 0 in your output table, which is here. It kind of like broke into two rows for each of the record. So here you will see the category content, that is the initial data frame we started with. Then you find words after a pipeline stage. Then you get the filtered words after stopword removal. Then you get the raw features using the hashing term frequency. Then using the features with IDF calculation. Then you create. Then you have the label feature from the category, converting the categories with string indexer. Then you get raw prediction, probability and prediction from the classifiers output. Now once you have loaded the data, you split it into train and test data and design your pipeline with regular expression tokenizer, stopword remover, hashing based term frequency calculation, inverse document frequency calculation, and converting the category into labels, so that the naive Bayes as a classifier can recognize which of the columns to work on. So features and the label needs to be specified to naive Bayes work properly. And again, this is a multi-class classification, so the model type should be multinomial. You organize the pipeline into different stages here, and you do the training with the training data using the pipeline.fit method. You gather your predictions for the test data using the pipeline feed.transform method, where you will show the predictions and also calculate the accuracy with the prediction table or the data frame. Here we are going to do the multi-class classification evaluator with prediction column equals to prediction, and the metric name will be accuracy. we calculate the accuracy and it should be saved in the accuracy_training.txt file. So if you open the accuracy training.txt, your number of test instances was 520 and the accuracy on that test data was pretty good, actually 95%. After that, we have generated the models, but we need to save it for later use. Here we are saving the model we have just created to a folder, pre-process fitted pipeline saved. It should be available in the same directory where the training.py is, and when you expand the folder, you should be able to see two different folders like stages and metadata. If you expand the stages, you should be able to see the pipeline stages defined within the model. So once everybody is comfortable with this program, we will move on to the running the next program, which is, in our case, it will be Kafka trial.py, which will act as a consumer for the generated messages through Kafka. Let's focus on the Kafka trial.py now. I will request you to start focusing on the main portion of the code first. At the very beginning, it says that there is a certain way to run the Kafka word count. So basically, with the label map, we will be keeping a map on the integer to section name mapping, so that we can do visualization better. Otherwise, you will be in the output, you will be only seeing the numbers. It will not be very meaningful which section it belongs. So starting with the with line number 72, we are creating a Spark context, and we are also using a feature on a Spark context, that is broadcast, where if you have multiple worker nodes, you want to share a particular attribute with them, you can use this feature. You can broadcast a particular attribute to all the worker nodes, so the worker nodes will be able to access that attribute and its values. Then we create the streaming context. Here we specified the window size to be 20 seconds. So on every 20 seconds, it will do the processing job on the collected data. We initialize the Elasticsearch, and we also create an Elasticsearch index with name article that will be used with Kibana to do the visualization. So you can think of Elasticsearch, it is within this context, it can be think of as a database, and your index, name of the index is the name of the table. So you continuously put data into the table, and on the front end, Kibana will be able to capture the new generated data and do the processing. I think before going to this part, Shihab will explain how Kibana and Elasticsearch works, so that you can get a better picture on the visualization part section.
So we'll be using Elasticsearch and Kibana today and also tomorrow. So it's better if we know a little bit about it. So basically, Elasticsearch is kind of like a database where you can store your data. An open source distributed search and analytics engine based on Apache Lucene. So on the background, it runs Apache Lucene, and it is distributed in nature, and it can do all kinds of analytics, and it has a strong search engine where you can search your data and do any kind of analytics. So it provides first and real-time search and analytics for all types of data. It can handle n types of data, kind of like a NoSQL types of database. So structured or unstructured text, numerical data, or geospatial data, and many more. So document-oriented database designed to store, retrieve, and manage document-oriented or semi-structured data. So it actually has its own domain-specific language in which we specify the query in JSON format. So it does not have any structured query language or anything. You use their APIs or their specific language and query in a JSON format to get the data or retrieve the data or store the data. These are some of the common usage of Elasticsearch. Log analytics, full text search, security intelligence, and also you can build your kind of behavioral model on your data using machine learning also. So how does it work? So send data in the form of JSON documents to Elasticsearch using their API calls, stores the data in original document, and adds the searchable reference to the document in the cluster index. So basically, they use the inverted index mechanism to store all the documents. So when you have multiple search nodes in a cluster, the stored documents are distributed across the cluster and can be accessed immediately from any node. So when you have multiple nodes, all the documents are distributed in many clusters around different nodes. So that's why it is distributed. You can search and retrieve the document using the API calls. And so this is basically a database, so you can actually visualize your data. So for that, you can use a tool called Kibana. So Kibana is also from the same vendor, which is Elastic. So you can use Kibana, an open source visualization tool with Elasticsearch to visualize your data and build interactive dashboards. So it's really handy when you do any kind of projects, especially data analytics types of projects. So we'll learn a little bit about Kibana. An open source data visualization and exploration tool lets you visualize your Elastic data. So you can search, view, interact with the data stored in Elastic indices or the database. So you don't need to actually install any app for that. Like you can just access it through your browser. So for that, you can access the Kibana from localhost. This is the 5601 is the default port. If your Elasticsearch is installed in your local system, then you can just use the localhost. Otherwise, you have to use a server domain. So for visualization, it has lots of some options. You'll get lots of options here. For example, you can view your data in a histogram format or line graphs, pie charts, and etc. So connect Kibana with Elasticsearch. So you already have your database in your system. You just connect your Kibana with Elasticsearch. For that, you have to go to the localhost or your domain and on the port 5601, and you have to specify an index pattern. So index pattern is like it's almost like a database name. So when you create your database, you name the database, like you name the table. So here, in Elasticsearch, there's no table, but all the documents are referenced using an index pattern name. So you have to specify index pattern name. We'll show you how it is done. Create the index pattern to add the index pattern, and Kibana displays only read-only list of fields configured for the matching index. So when you specify that index, it will fetch all the data that are referenced through that index, and it will show all the data. So when you get all your data, so you can iteratively search and browse your data from the Discover page, chart and map your data from the Visualize page, and create and view custom dashboards from the dashboard page. So this is basically the Discover. You can see your data in this Discover page. So this is basically the IoT data that we gathered. You will see this project tomorrow. You can also run the project. So when we gather the data, we save it in Elasticsearch. These are the formats. You can see VOC means the hum means the humidity. TMP means the temperature. CO2 means the carbon dioxide level. All these things. So it's a IoT sensor of it can manage. It can send. It's a sensor. So it is an air quality monitor sensor actually. So it can measure the temperature and the humidity level and the carbon dioxide level also. So in the visualization page, you can actually view your data in a different kinds of format, like pie chart, or like here it's a bar graph. So there are lots of options. So you can select the options and just view your data and analyze it according to your application. And dashboard is a collection of visualizations and searches and maps, where you can store all your visualization charts in one place. So So as the Elasticsearch is already running, I guess you already ran the Elasticsearch for the commands from the README file that site showed. You also ran the Kibana also, so it's already running in your system. So you can just go to localhost and colon 5601, and this is the Kibana interface. If you go to the Discover, there are already some data stored in your Elasticsearch from the previous runs. So this is the index name. That under this index name there are data. So these are the data that are referenced through this index name. As it is a search engine, you can also search stuffs. So, for example, maybe we can search the prediction, which are just one equals some value, update. So you can just search. So I'm here searching the data instances that have prediction 1. Okay, so to visualize, there you can also visualize. For example, here, what is it? So this is the prediction level. So you can see the percentage of prediction levels in the data. Business has more, politics is 10.2%, media 2.3%, society 2.3%. Does anybody have any questions on Kibana or Elasticsearch? So Kibana only works with Elasticsearch. There is also another tool, visualization tool called Grafana. It can also work with Elasticsearch, and Grafana I think also works with MongoDB. So if your database is MongoDB, then you can use Grafana, which is I guess. This is Grafana. But for here, as we are using Elasticsearch, we will be using Kibana as our visualization tool. So I think now Saeed will run the third hands-on, and show you the visualization of the output.
So basically, as he has shown this this visualization tool, let's start from here, because you have seen already there are already some pre-populated data. So we want you to have experience on a fresh data set. To do that, if you go to the select, like the management and index management, you should be able to see there is an index named article. Manage index, you can delete this index if you have one, otherwise you are good. Again, if you want to delete a particular index, from the management window at the bottom, select index management, select the particular index you want to delete, and simply delete the index. So we will be focusing on the Kafka trial py that acts as a consumer for the messages generated by the stream producer.py. So it will work on a streaming context with 20 seconds of window, and as we have seen that there is an Elasticsearch helper class. The index will be automatically recreated with this command Elasticsearch indices.create. Then we will load the pre-processed fitted pipeline saved model, which we have populated in the previous offline training with the offline training code. We also know about the Zookeeper instance location and the topic we want to focus on, which in this case it is guardian 2. We will create the stream using Kafka utils and the necessary parameters like the Spark streaming context and the zookeeper address, also the topic.
I don't seem like I have the right sync file. I may not have the right file.
We both might not have.
Yeah, we both may not have the right file.
Where you downloaded from?
Um,
Can you go down?
yeah. Okay, here it is. That's the 20.
Yeah.
Okay, okay.
Yeah,
okay.
yes, down.
Okay.
Down to the, okay. So now on your Kafka messages will look like this. So each message from the producer is basically a single line containing 3 sets of information: the category index, the actual name of the category, and the content of the file. With this KVS map operation, we are creating tuples that becomes like this. So basically this one is your category index, again business is your category name, and this is the content. Then for each tuple or each RDD in the document tuple, we call the process method, which you will find at the top. Here we are creating a data frame with 3 attributes, basically category, string, label, and the content. So this becomes the category, this becomes the STL label, and this becomes the content. And this is your Spark data frame. Then we call the model.transform method that we have preloaded with the data frame we have, and we show the predictions in the output window. After that, we will use the multi-class classifier evaluator with label column. As you can see, the category is the label column and the prediction column will be the prediction from this predictions data frame, and we will be using accuracy calculation for as a evaluation metric. So with this and we will be collecting the accuracy data on accuracy.txt. So in this file you should be able to see multiple lines with each line reporting accuracy on a particular time window section. This many records came in, and the classifier accuracy within those documents is that much. There is already, I think, some pre-populated information. Yeah. There should be. So at a particular window, 31 instances came, and it performed very bad. And with single instances, it achieved this. I mean, almost. Yeah. It predicted it correctly. So 100% accuracy. So once you run the program, you should be able to see this file. It is generating a single line reporting the accuracy for each of the time window. So now we have shown the accuracy in a file, but to save the data for Elasticsearch, we will go through the each entry for the prediction table, and we will do the mapping because prediction is integer. We have to map it to corresponding section name. Then we will create a JSON object including all the information we want to see in the front end, that is category, label, prediction, and the predicted label. So category will be an integer, label will be the corresponding string representation like business politics, prediction again it will be an integer or I mean whole number, and predicted label will be the corresponding section name. Again we are specifying the name of the index to be article, and the type of the entry is document. You also keep ID for each entry, and we use a incremental index. You will see that index is incremented after each insertion. Yes.
So I know there's like a Elasticsearch plugin for Spark directly.
Okay.
Ever use that?
No.
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 Okay.
Yes, Elasticsearch bucket for Spark directly means.
Yeah, like there's an API for Elasticsearch with Spark. I've tried to use it once and I never could get it to work, so I was just wondering if you've ever.
Oh, I don't have any experience with that working in that manner.
Okay.
So.
Yeah, like versus like what Spark is Elasticsearch directly. Yeah, so like another like so here you're talking your two Elasticsearch in Python, like so what's then
There are other ways, yeah. We haven't tried that.
I just never did it.
Some other visualization. These are open source.
And we hand over the helpers class with the actions so that it can be it does the job for insertion to the index, appropriate index for Elasticsearch. So basically within the database context, you are inserting into article table, and you will have this many fields for a particular row. So to run the program, we will copy the command from the README file specified in the Google Doc, and that will be this command: Spark submit packages org Apache Spark streaming Guardian 2 without the quotes actually. Quotes. So I'll run it from the terminal within the PyCharm ID. Yes. So once it is running, you will see that at some point of time it generates new output, because that time it started it processing. It starts process. I mean, every 20 seconds you should be seeing new outputs here, because it tries to process the incoming data. But we are not still providing any data to it, which we will do through stream producer. Now, in real scenario, we will have a stream producer that will be running all day long and collecting data and streaming through the pipeline. But to make it manageable within short time of period, we have designed a simulated streaming producer where you will collect the data from past 10 days, store them first, then kind of like every 1 second you will send one message. So it will be slow, and on the front end it will be easier for you to visualize that some changes is happening throughout the system. So the stream producer works in similar manner to get data. So whenever you specify, so for example, in this case I specified 4, now I will make it 10. So it will gather 10 days of data, and after collecting the data, instead of storing into the file, it will send to Kafka for processing. So the key area we want to focus on here is the data collection part, and here you get the data corpus populated, which will contain all the documents downloaded. Now, to communicate with Kafka, you have to first connect with Kafka producer from your program. You will specify the necessary parameter like the Kafka server location, and once you have the Kafka producer instance in your program, from each story in the data corpus, you will be publishing messages through Guardian 2 through the Kafka API. Here you will specify the topic name to be Guardian 2, so that the other consumer be able to find the corresponding message. And I have commented out the time.sleep for 1 second. You can uncomment it so that it runs slowly, and you can see the changes. So to publish message, we will be using the publish message method defined here, which basically uses the producer instance to send the message into particular topic. Here we are specifying key bytes to be foo, a particular fixed key, so that all of them goes to one partition. There is no need to think of partitions here. Okay, I think there will be 2 seconds of delay. Okay, in this scenario there will be actually 2 seconds of delay, so you can keep it or you can remove either one of them, because inside the publish message there is also a sleep called, so it will eventually do the same thing, slowly publish the message. Now the process is running to consume the data. We will run this program to produce the data and send it to the consumer and try to see the visualization on the front end. To run the program, just simply run stream producer, run stream producer. So it started collecting the data. And it has been starting sending the messages. If you open the terminal, you should be able to see that process has been started grabbing the articles, like push block input 0. That means a particular, a news article has been added to the memory for processing at time window. If you go to the front end to visualize, hit Kibana, inside index management, no, go to the discover section, and there is no article specified. Okay, I think you have to go to the home page. Localhost 5601, then you select the index pattern, and from there you create the new index pattern, specify it as to be article. It says that I have a success, I have a match with one index. So I'll hit the next step and complete it by clicking the create index pattern. It will show me the how each attribute, each record under the article index looks like. So you have the ID, index name, type is a document, and these are the values we are mainly interested in. That is level keyword, predicted level, and predicted level dot keyword. So after you have created the index pattern, go to the discover section where you will find your newly indexed pattern to be listed in the drop down menu. You click it and you should be able to see new articles has been coming in. These are record for each articles. I think I need to, you should be able to see, right? So each record looks like this. It has a category and the index name, level, predicted level is society, but prediction is 1. So this, in this case, the prediction is wrong actually. So this is one record. Now when you do the visualization section, go to visualize and create visualization with a plus button. I can show you with the tag cloud and select the article index you want to measure on, and buckets. Okay, so again from the beginning, select visualize, this visualize, and select the plus button to create the new visualization. I am using tag cloud to demonstrate, and I am selecting the article index. Select bucket type is tags, aggregation should be terms. Select a field, you can select the label keyword, it will show you the distribution of the classifiers. So, this is the distribution now. It will, if you hit, if you do, sorry, you can schedule it, refresh every say 15-20 seconds, it will refresh and start the visualization. I am not sure it how it look like, because still there are some portion to come. So, time to time when the new entries come, the visualization should automatically change the distribution. But why there is time? So, I
So I think you can take another 10 minutes break.
yeah, it is automatically changing every 20 seconds. So,